This is Francine. She's going on a boat ride in the ocean. She gets out her phone to take pictures, and oops, she drops it in the water. The phone falls down 50 meters. Fortunately, Francine did get a case for her phone, and that case will protect her phone to a pressure of 5 atmospheres. Will Francine's phone make it? We can figure out the pressure at some depth D, and that depth is from the surface of the water to where the object is, in this case the phone. To find the pressure, we're going to look at the forces that are acting on the phone. In this case, it has the force of, first, it has water from the bottom pushing it upwards, and we'll call that force of water up. We also have the force of the column of water that's above the phone pushing down. So you can imagine this column of water, the weight of that water is pushing down on the phone. So we're going to call that force of the weight of water. We also have one more force, and that is something we don't always think about. But on top of this column of water, there is air molecules. We'll assume the boat is not above the phone to keep it a little bit simpler. But we do have the weight of the atmosphere pushing down on the phone as well. So we're going to add another force, and we'll call it F naught. We used P naught to refer to atmospheric pressure. We'll use F naught to refer to atmospheric force. So we have three forces: the force of the weight of the water, the force of the atmosphere, those are both pushing down on the phone, and then we have the force of the water acting up on the phone. In this case, this is an example of hydrostatics. Hydrostatics is when a fluid is at rest. You can see the roots of the word hydro is the fluid, and static means not moving. So in this case, we'll assume the ocean is, for the most part, not moving. It's not going to be pushing the phone around. We want to figure out what is the pressure at that depth. Since the object is not moving and it's in a hydrostatic state, that means that the sum of the forces is going to be 0. If the sum of forces is 0, that means the force going up on the phone is equal to the forces going down. The force of the water up equals the atmospheric force down and the force of the weight of the water. Now we're actually looking for the pressure at this depth. So we have to remember our equation for pressure. And remember that pressure is not equal to force. So since pressure is equal to force over area, we can replace force with pressure times area, because this equation can be rearranged to be PA equals force. So the force of the water up equals the pressure at that depth times the area, and the area is going to be the area that the force is applied. We'll just consider this area of the column, because we're finding the overall pressure at that point. So we'll consider the area of that column. For the atmospheric force, it's going to be the atmospheric pressure times that area. We're going to leave the weight of the water using mass times gravity, because weight is defined as mass times gravity. We're not going to use pressure because we don't know anything about the pressure of this water. So we're going to make it mass times gravity is our weight, and that is going to be the force. So now we have the pressure, this is the pressure we're looking for, times this area equals the atmospheric pressure times area plus mass times gravity. We're going to simplify this a little bit more. We don't know the mass of the water, but we can use what we do know about water, which is its density. So I'm going to make a little review here of density. Density we write with the Greek letter rho. And density is equal to the mass of something divided by its volume. So the mass of the water is going to equal the density of seawater times the volume that we're talking about. We're looking at this mass right here, so that's going to be this volume here. So we can rewrite density as density times volume equals mass. And now we're going to take this and plug it into our equation. So we get P times A equals P naught times A plus mass, which is equal to rho V times G. We're going to simplify this even more, and I'm going to take the density equation off so I have space to do that. We're going to simplify it by noting that the volume of this water is equal to the area times the depth. And we can use that to plug into here. So we still have PA equals P naught A plus rho, and the volume is equal to area times D times G. And you can see why I did that, because now we have area, area, and area. Because in fact, at any depth, it doesn't matter the area of the water you're looking at, you're going to have the same water pressure at any depth. So now we can cancel out area. And we end up with our equation for pressure at depth. And this is an equation that you will be using for pressure in a fluid. The pressure at any depth is equal to the atmospheric pressure above it plus the density of the fluid. So make sure you remember that this is the density of the fluid times the depth times gravity. And that is our standard equation. Now let's see if Francine's phone will make it. Here's our equation. We want to find the pressure at this point, because this pressure can't be more than 5 atmospheres, because that's all that's safe. So we're going to have atmospheric pressure plus rho g d. Atmospheric pressure is 1 atmosphere. In this case, we're going to be using a depth in meters, so we're going to use our atmospheric pressure in newtons per meters squared. And our atmospheric pressure, 1 atmosphere, is equal to 1.01 times 10 newtons per meter squared. So we will put in 1.01 times 10 to the 5th Newton per meter squared. Now we need the density of water, and she's in the ocean. Some typical densities of fluids. You can see that water is 1,000 kilograms per meters cubed. Seawater is 1,030 kilograms per meters cubed. Since she's in the ocean, we're going to use a density of 1,030 kilograms per meters cubed. This is multiplied by gravity, which is 9.8 meters per second squared. I can't fit it here, so I'm just going to squeeze it in. We're also multiplying by the depth, and we said that her phone fell to a depth of 50 meters. So this is times 50 meters. So our pressure will be 1.01 times 10 to the 5th newtons per meter squared plus 5.05 times 10 to the 5th newtons per meter squared, and all of that is 6.06 times 10 to the 5th newtons per meter squared. That is the pressure at depth. Well, we don't know it in newtons per meter squared, we know it in atmospheres, so let's get this into atmospheres. 6.06 times 10 to the 5th newtons per meter squared times 1.01 times 10 to the 5th. This is the conversion from newtons per meter squared to atmospheres. And we get a pressure of 6 atmospheres. So her phone has gone to a pressure of 6 atmospheres. The case will not survive, unfortunately. The good thing is she did buy accident insurance, so she can get it replaced.